Okay, happy Easter, happy post-Easter Year 12. This is the first video you need to watch for next term. If you're watching it before the lesson starts, well done, you're on to a winner already for this term. So, in the following video, you need to do the following things. You need to recall how to draw force diagrams, you need to be able to state Newton's laws and describe what they really mean, and you need to be able to apply a logical structure to answering questions on Newton's laws. Most of this should actually be recap of GCSE, but in this short video I'm going to go through the basics of what you need to know for the next few lessons. So, first I want to remind you that vectors can be represented by an arrow showing magnitude and direction. This is important because we're going to be talking about forces, velocity and acceleration in this video, all three of which are vectors. Therefore, as forces are vectors, you need to remember the following when drawing them. The direction of the arrow tells us the direction of the force, the length of the arrow tells us how big the force is, and the position tells us where the force is acting. And it's this one that you might need to be a little bit careful about in some of these examples and questions. Please make sure you're showing the position in the correct place. So, for example, whilst this is a big push to the right, nice big arrow, this is a small pull to the left. So the size, the length and the direction, the position of the arrow, they're all important things. So how can a force affect an object? Well, there are three ways a force can affect an object. First one is by changing the shape of the object. This is to do with elasticity and plasticity. That's all that material science we did back in January and February. I suggest you go and recap that if you're not sure what I'm talking about. The second thing is a force can change the direction of an object, so the direction that it's moving in, but a force can also change the speed of an object. And of course, the more savvy amongst you will have noticed, well, direction and speed, that's really just two simplified ways of saying that forces can change the velocity of an object. And Newton's laws talk about the effect of forces on the velocity and acceleration of objects. So here are Newton's three laws, briefly summarised for you. The first law says an object will either remain at rest or at a constant velocity unless it is acted on by a resultant force. It's important to note here that at rest is really just a special case of constant velocity, because 0 meters per second is just constant, no velocity, zero velocity. Newton's second law says that force is equal to mass times acceleration. Now you've already used this a lot when calculating weight, because weight as a force is equal to mass times acceleration due to gravity. That's a specific case of the more general second law, force equals mass times acceleration. The third law is the one that is perhaps the least understood by most students, but it's really very simple. It just says that for every action force on a body, there is an equal and opposite reaction force. If there wasn't an equal and opposite reaction force, I would be able to put my finger through the table when I apply the force from my finger on the table. Or as I'm sat on this seat now, if there wasn't a reaction force from the seat, I would be falling through it. I will go through some more examples of third law later on. But let's start by talking about first law. So in an old-fashioned sense, first law was normally called the law of inertia. We don't really call it that anymore, but it was a nice description of what the law was. Essentially, inertia is the tendency of an object to resist changes in its velocity, whether it's in motion or it's motionless. So in other words, an object will try to continue at a constant velocity unless you can force it to change. Now, we tend more now to talk about momentum. Inertia really is an old-fashioned term. But inertia is a nice way of describing what first law is saying. So for example, these pumpkins will not move unless they're acted on by an unbalanced force. I literally have to force objects to change their velocity. Now these resultant forces influence motion in various ways. Generally, for an object that is already in motion, so it has a velocity, if there is zero resultant force acting on the object, the velocity will stay the same. It won't accelerate, it won't decelerate. If the resultant force is in the same direction as the motion of the object, the velocity will increase, so it will accelerate in the direction of the resultant force. And if the resultant force is in the opposite direction of the motion, then the velocity will decrease. Note, it will not immediately accelerate in the direction of that resultant force. Instead, its it will decelerate in the direction of that resultant force until the velocity comes to 0, at which point it will accelerate. Now, I've already said that stationary is a special case of an object travelling at a constant velocity. So 0 resultant force on a stationary object, well, the velocity will remain 0. If there is a resultant force in the positive direction, the velocity will increase in that direction of the resultant force. And this time, because it's already at 0, if the resultant force is in the negative direction, so the opposite direction, it will just accelerate in that direction. This is because it's already at 0, so it cannot decelerate. All it can do is accelerate. I'll say it again, stationary objects are just special cases of objects under constant motion. Now, I wanted to show you some force diagrams in order to relate this for you. So here I've got a ball sat stationary on a surface. It's got its weight acting down, and due to Newton's third law, there's therefore a normal reaction force pushing back up. The sizes of the arrows are the same, so there's no resultant force. The object is not moving, so there's 0 velocity and 0 acceleration. But what happens if I come along with my finger and I push the object to the right? Now I have got a resultant force acting on the object to the right, so I'll have a velocity and an acceleration moving the object in the direction of that resultant force. What happens now if I'm pushing the object and suddenly it experiences a backwards force? So something is pushing against my motion. The overall resultant force will be to the left. So whilst it will still be moving to the right, it will be starting to slow down because of that resultant force in the opposite direction. So the acceleration will now be in the opposite direction and the velocity will start to decrease. The acceleration or deceleration is always in the direction of the resultant force. Take another example, a pebble being dropped from a bridge. Now it's initially stationary, I'm just dropping it, I'm not throwing it. The only resultant force acting on it is a downwards resultant force. Therefore its velocity will be downwards and its acceleration will be downwards. Because it was initially stationary, it experienced a resultant force downwards, so it will start to move downwards. What about a baseball being hit at the air at the moment the bat hits? So at the moment that the bat hits, there will be a force upwards from the baseball bat acting against the weight of the baseball downwards. And you can see that the resultant force is going to be in the upwards direction because the force coming from the bat is larger. Therefore, the velocity of the object will start to be upwards, which means it will accelerate in the upwards direction. It was initially stationary, but I get a resultant force upwards, so there'll be a velocity upwards and acceleration upwards. What about when it's midway through the air? So it hasn't reached the top of its path yet, but it's no longer touching the baseball. Well, the only force acting on it now, if I ignore friction and air resistance, will be the weight acting downwards. There's no other force. It's no longer in contact with that baseball bat, so there's no force anymore from the baseball bat. Because my resultant force is now downwards, the acceleration will want to act in the downwards direction. But the ball is currently travelling upwards. So there'll be an upwards velocity, which is actually getting smaller, and there will be a downwards acceleration, or in other words, there will be a negative acceleration in the downwards direction. It is decelerating downwards. Once the baseball reaches the top of the arc, so it reaches that point where it turns around and starts to fall back down towards the bottom, there is still a resultant force due to the weight acting. There's no other force, just the resultant force due to the weight. Its velocity is actually 0, it's at a stationary point, but it is now accelerating. It will now start to accelerate down towards the bottom. So it's instantaneously stationary, the resultant force is downwards, we've reached the point where the velocity is now 0 because it's decelerated so much, and so it will start to accelerate downwards. Now, I'd like you to vote on this one. This is the baseball when it actually strikes the ground after being hit. What do you think will happen to the resultant force, the velocity, and the acceleration? Okay, so as it hits the ground, the weight will be acting downwards, and there will be a normal reaction force upwards. I apologise, I got those arrows in the wrong direction. It will be instantaneously stationary, so the velocity will be 0, but because it has now decelerated from moving downwards to being stationary, there will be a negative upwards acceleration. So it's decelerating, in fact it has decelerated, and it will be decelerating upwards. But how do we know what force the ball exerts on the ground? Because obviously the force it exerts is quite important. If that was a window instead of the floor, how would we know if it would break the window? That is Newton's second law. So Newton's second law said that force is equal to mass times acceleration. When mass is in kilograms and acceleration is meters per second squared, the unit of force is in newtons. What this allows us to do is it allows us to define what a newton is. 1 newton is equal to the force required to accelerate 1 kilogram of mass at 1 meter per second per second. Probably worth noting down those two statements. Now, second law really proves that different masses accelerate towards the Earth at the same rate, but with different forces. We know that objects with different masses accelerate to the ground at the same rate. If you don't believe me, I will show you this in lessons, but it might be worth Googling it. There's some quite interesting experiments. Because of second law, we know they don't hit the ground with the same force. So if I drop a metal ball bearing and a medicine ball, one of them will make a dent in a baking tin and the other one won't. The reason is that the force is not the same. So here I've got a 10 kilogram mass. The force due to gravity will be 9.8 times 10 kilograms, that's 98 newtons. So the acceleration will be 98 divided by 10, that's 9.8 meters per second. If I take a smaller object of 1 kilogram, the force due to gravity will be 9.8 newtons, which means the acceleration will be 9.8 divided by 1, that's 9.8 meters per second squared. In other words, acceleration due to gravity does not depend on the size of the object. Again, I will show you this in lessons if you don't believe me. Just a little of note, Newton's second law anew. Why should you really care? Well, because of first law and inertia, objects resist changes in their motion. So when the car is moving at 80 kilometers per hour and it's stopped by a brick wall, your body will keep moving unless you are wearing a seatbelt. Quick quiz, assuming you weigh 100 kilograms, if you do hit the wall and then stop, how much force will you exert on the wall and the wall on you? So using F equals ma, we can say that if your mass is 100 kilograms and you're going from 80 kilometers an hour to 0 kilometers an hour, 100 times 80, that's 8,000 newtons that you would exert on the wall and the wall would exert on you, which is pretty damaging. In other words, wear a seatbelt. Right, quickly, third law. For every action, there is an equal and opposite reaction. If you watch The Big Bang Theory on E4 much, you will have seen this in one of the adverts. It's often stated, but a lot of people don't really understand what it means, so I want to show you some examples. Here, the action is the tyre pushing on the road due to the driving force from the motor, and the reaction is the road therefore pushing back on the tyre and providing that drive forward. The rocket, as the rocket pushes out on the gas then pushes on the rocket and forces the rocket forwards. If you let go of a balloon, the force of the balloon pushing the gas out gives a reaction force of the gas pushing back on the balloon and sending it forwards. When you pull on a spring, the spring pulls back on you. If it didn't, you would fall over. And when the earth pulls on a ball when you let it go, the ball actually pulls on the earth too. Gravity is an attractive force between objects. It doesn't just act in one direction. I will go over third law again in the lessons if that's confusing. What's more important is that you know how to structure an answer. So here are my kind of 10 guidance points for answering a question on Newton's laws, in general for answering any mechanics question. Number 1, check you know what the topic is, and then draw a diagram. Even if they've already given you a diagram, can you simplify it? We did practice this when we were doing moments calculations. It is really important that you can simplify those diagrams. You then either need to label or list what you know. For example, list the forces that they've given you. And state also what you're trying to find out. If you know the symbols or the words for what you've got and what you need, you will be able to work out what equation to use. You can then substitute everything into your equation, find your answer, check you've got your significant figures correct, and add your units. I would strongly recommend writing down these 10 points to check that you have done and that you can actually use them. Here's a quick question. So this is an exam question. You need to calculate the average acceleration of the train and the average tension in the cable that is accelerating the train. I would like you to bring your worked answers to this following the 10 points to our next lesson.